222. And it's asking the greatest height of a rock as measured from the base of the cliff.
Okay, and they give you the initial velocity?
Yeah.
Okay.
Well, you found it in part A.
Okay.
And it's 14.6, and the height of the cliff is 32 meters.
And the height of the cliff is 32 meters?
Yeah.
And this is launched upward from the cliff?
Yeah. Well.
From the cliff?
It's thrown up from the top of the cliff in part A, and then that's.
And then it comes back. So is this what's happening right here?
Yeah.
Yeah.
Okay. So the initial velocity that it's launched with is 14.6 meters. That's what you got?
Yeah.
Okay. So at the beginning it has what kind of energy? Since it's thrown? Kinetic. It also has potential energy due to its height. Now, part B said determine the max height with respect to the cliff, correct? So I would consider for part B, I would call this PE equals 0 for part B. So that I don't have to worry about any potential energy. Because remember, part B starts at the cliff, and where does it end? No, part B, you said find the max height, right?
Yeah.
You said for part B, find the maximum height?
The greatest height of the rock as measured from the base of the cliff.
From the base of the cliff. Okay, so if we consider this ground level, we figure out the height here, and we can just add 32 to that, right?
Yeah.
So what kind of energy does it have at the top?
Potential.
Potential. So we have potential at the end of the problem. So this is the end of the problem right here. That's where it ends, where the red dot is. Again, the key to a lot of these problems is to recognize where's the beginning, where's the end. We're trying to figure out the height when it reaches its apex. So that's got to be the end of the problem. Then we add 32 to that value. Does that make sense? Did others do it this way? Did you get an answer? Oops. If we look at this, we have KE initially. We have potential energy at the end of the problem. This comes from this. And Gabe said he determined the initial velocity earlier in the problem. Do you need the mass?
No.
Why don't we need the mass for this?
It's not a mass dependent.
Very good. That's well stated. It is not a mass-dependent answer. Very good. So that reduces on both sides or cancels. So we solve for YF. That'll give us the height when it's at its apex from the cliff. And to that, add 32. Again, what are we solving for in this problem right here? This is what we're looking for, okay? YF. That segment in blue at on the diagram. That would be, what is that? 1/2 VI squared over G. Does that make sense how you would do that? If you're trying to find the total height as measured from the base of the cliff, here's the base of the cliff down here. Here's the cliff itself. It's getting up to this height. So measure this height along this ground level, find the potential energy at the top, setting it equal to the kinetic energy with which it's launched. And this is thrown up, right? I did draw the diagram correct? And then add 32 because that's where the base of the cliff really is.
I also have a question.
Yeah.
I actually had like a couple questions, but one of them was for problem set 6.2.
Okay.
On page 206, number 29. And I don't have a picture of the problem.
Anybody have it written or a picture of it real quick in their iPad?
Something about a picture of throwing the ball.
A pitcher throws a ball?
Yeah.
No, Anthony has it. Just look at page 206, number 29. This is going to all be recorded, though. If you want to get it, see him later. Find him during the day in school, and you can get it for sure. No, but I have some in the office if you want to go next door and get some. You know where my desk is in the office? Right above my desk is a box. Who has the question? Oh, Annabelle. Awesome. What do you got?
Pitcher throws a baseball at 40 meters per second, 90 miles per hour. And the catcher stops it in her glove. Is the work done on the ball by the catcher positive, negative, or zero?
Okay. This is a theoretical question. I like this. So is the work done by the catcher positive, negative, or zero? Explain. But the explanation is what makes your answer right or wrong, actually. Because I personally think there are two correct answers to this question. Let me hear one of them. What did you think it was?
What first I thought it would be negative, since the ball is happening because you're stopping it. Because doesn't that count as movement?
So that's the question right there. Do you hear that?
There's backwards movement.
Does the catcher's glove move back? Does it say it in the problem?
No, it doesn't.
So that's how you have to interpret it. So here's your answer. Either
I said 0 because there's no velocity in the catch. When you catch it, there's no movement, so there can't be work.
okay, but he's saying, be careful. So what you're saying is that because the catcher's glove doesn't move, there's no distance traveled, so the force you're applying against motion occurs over no distance. I could accept that if you said no distance, not no velocity. Because there is a change in velocity which could be incorporated.
I mean, I said 0, but I viewed it like in the perspective of the ball because he's stopping the ball, he's not moving the ball. So
Exactly. So that's acceptable if you viewed it that way and you gave evidence. Now, what's another interpretation? Because there's another right answer for sure. It's based on your interpretation and the way you explain it.
I don't know if this is right or not, but I said the work being done on the ball would be negative because the glove is kind of like a negative force that usually stops it.
Okay, you're on the right track because you're right. The glove pushes back, right, against the ball, and the distance the ball would travel, if the glove moved, would be this way. If the distance is this way and your force is this way, what's the angle? 180. So it's like work done by friction if you think about it. So you're right in the sense that your force is negative or opposing motion, but you would want to be specific and say, and the glove travels a certain distance back, because work can only be done when a force is applied over a given distance. So the interpretation is about whether the glove moves or not. If the glove moves, you do work. What kind of work? Negative work. Because again, the glove and the ball would move this way, and your force would be this way. This is a 180-degree angle. Okay? Yeah.
So since it doesn't say that the glove moves back, could we just?
You would have to explain yourself.
Oh, so we would explain. Okay.
That's why it says give reasoning. Okay?
On a test, will there be, for a cosine theta, will that only include angles 0 and 180 unless otherwise?
Yeah, unless otherwise stated, an object is pulled at an angle of, or a pulley system lifts an object out of a hole at an angle of. Okay? Remember, the angle for work done is always between the direction of motion and the applied force. So remember, think about there's a hole in the ground, okay? I'm pulling on a cable. I'm trying to pull on this cable. Which way does the object move if it's coming out of a shaft, like a mine shaft? The cable itself, I mean, yeah, up and to the side. Which way does the object move, though? Straight up. So the object's moving this way. Listen, guys, you're pulling on the cable this way. So you're pulling on a tow cable at an angle, but it's moving up. So this is your angle right here. That's theta.
That would need to be given.
That would be the angle given, yeah. Now, if you're pulling on an object that's on the floor, the motion is to the right. You're pulling it this way. This is the angle right here. You see the difference? This is like an angle with the horizontal, whereas the other one, the object was moving up, this was the pull, this is an angle with the vertical. All that matters is that you measure the angle with respect to motion. So the force, whatever that's applied at, and the motion, whatever angle they make.
But like
Horizontal motion, pull, vertical motion, pull.
But like if you had like a light ball, say, and the wind is pushing it, that would mean this is this friction going that way and going that way. That's an 80 direction.
So wait, an object is at rest initially,
Yeah,
and the wind comes through to push it.
Yeah.
Well, the wind is pushing it that way, it's moving that way. Wind does positive work in that
so
case.
it's all in that direction, then 0.
If the wind was perfectly horizontal, those are big ifs, right? Again, the angle theta would be 0 in that case. But if you're given the wind is coming down at an angle of, then you'd have to actually use that in the problem.
So if there's two opposing forces coming, that would be.
If there's two opposing directions, not forces. Remember, the direction is one vector, and the force is the other vector. It's the angle between them. So remember guys, look, this is a great question because this is where kinetic energy theorem we're going over right now. So this object, I push it across the table. I'm pushing it that way. It moves that way. So I do positive work. Okay? Now, again, I push it across the table. It's moving this way. Which way is friction pushing? The angle between this vector and this vector is 180 degrees. So therefore, friction does negative work on the object.
But by that case, because we're assuming that sometimes it's friction.
Correct. That's the key. If things are frictionless, you don't have to worry about that. Then in that case, almost all things do positive work for the most part, unless you're stopping motion.
But in the real world, it would always be 180 technically.
Friction?
There's always friction. Yeah.
Sure, but again, it depends on the scenario. Let's keep moving now. But yes, it depends on the scenario presented.
Can we go over page 222, number 100? This is another conceptual problem. I think
Page 222. Sorry, 202.
222.
222 and number.
100. This one meters.
Yeah, it's like a diagram.
Yeah.
Okay, so this is the one. I wish I could do this real quick. Just take a quick picture of this.
Wasn't it just like 4 parts you just had to write like correctly?
What are you talking about?
Okay. You want to give that back to? Give this back to Annabelle?
It's like a multiple choice
Thank you.
question. Wasn't
All right, so we're looking at number 100. We're looking at this diagram. 3 balls, they're thrown upward with the same initial speed. What does that mean? They all start with the same what?
Yeah.
Okay, what else? They're the same ball. Thank you. Kinetic energy. Remember, the problem begins with kinetic energy. It's at the ground and it's being launched. So they all have the same kinetic energy. Agreed?
Yeah.
Do you see what I'm saying? Okay, next. But at different angles relative to the horizontal as shown in the figure. Ignoring air resistance, indicate which of the following statements is correct when the balls are at the dashed level. At the dashed level. So what do we have to consider here? What's the difference here? Think about it for a second.
I guess 1 and 2 are still accelerating in both y and x, while 3 is stop accelerating in the y.
So, okay, let's say moving instead of accelerating. Correct. So 1 is still moving vertically. 2 is still moving horizontally and vertically. 3, though, stops moving vertically for that second, right? For that instant in time. Why is that happening again? What's the difference in them?
Obviously, I said it was A because if it's at the top, there's no kinetic energy, so we have no speed.
Be careful there, because ball 3 is still moving, but which way? Horizontally. So it still has kinetic energy at the top. Remember, guys, when we say an object has no kinetic energy at the top of its path, we're assuming it's tossed straight up in the air. Because when it gets to the top, it pauses and it comes down. But if I do this, when it's at the top, yeah, it pauses vertically, but it still has to be moving this way always. So it still does have some kinetic energy at the top. The question is, what kind of other energy does it have at the top there? What's the other type of energy, obviously? It has potential at the top, right? So at this location, it's got kinetic energy, it's got potential energy. The question is really which is greater, the sum of which of those 3. At each instant, it still has all 3 of those. It has all 3. So we've got ball 3 has the lowest speed, ball 1 has the lowest speed. All 3 balls have the same speed, and the speed depends upon their mass. Are we told that they're the same objects? 3 balls are thrown upward. Yeah, we're not, but it doesn't matter because if we solve, we know that what happens to mass in these equations. When we're ignoring air resistance, mass cancels. So the mass doesn't really matter, so we can rule out choice D right off the bat. Now the question is 1 or 3 the lowest speed, or do they all have the same speed at that instant? Think about it logically, come on. There's a simple answer to this, and we're all kind of forgetting about it. Right.
Were you asking A?
I'm asking you which of the 3 answers it is and why. There's a simple explanation.
What's it called? The third one.
Why you're saying choice C?
It has no speed.
So you're saying ball 3, Ryan? You're saying ball 3, or you're saying the third choice? You said the third
Well,
one.
I thought for this we had to do like, we had to pick which number.
Which of these is correct is the statement, which is true. So pretty much what it's asking is, what is the deal with the speeds?
Then A.
So you would choose A. Will?
I think it's C because if there's no air resistance, then the path of the ball won't matter. So it's only being slowed down by gravity, and they're all being slowed down by gravity, so they all have the same speed.
That's the key here, all right? And the idea is energy also. Think about energy. At that location, what do you know about their potential energies? Think about potential energy at that height. They're all what? the same. They all started with the same kinetic. Again, remember initially they all were thrown with the same velocity. So these KEs I'm writing down, you can call them 1, 2, and 3. They equal each other. Well, the PEs also equal each other because they're at the same height. So if you started with 20 joules of kinetic, and let's say 8 joules went to potential, how many are left? You started with 20, 8 joules went into potential energy, how many are left? 12. For all of them, it's okay. For all of them, it's the same amount of kinetic energy. They have the same masses. The masses actually, it doesn't matter because it's going to cancel out. So the velocity at those locations has to be the same. Okay? And the question says speed, not velocity, for a reason. Because speed is independent of direction. Tell me real quick, what direction are the velocities at each instant? Object 1, which way is the velocity still? Still vertical. There's my velocity vector for object 1. Object 2, though, it's at an angle. And object 3, we can see the velocity is completely horizontal. See what I'm saying here? Again, because it was kicked at an angle, the velocity here and the velocity here are actually identical. But this is all Vx, this is all Vy. So again, object 3 is all Vx at the top, object 1 is all Vy, but they're the same velocity. And then object 2 is in both directions, but again, the same velocity, or same speed, I should be saying. I was saying velocity because I was talking about direction there. But in general, all three have the same speed.
So if air resistance, like what, how would it change?
A lot of things could change this. Remember Anthony talked earlier about air resistance and also what's called rotational inertia? Both of those things play a role. So they both depend. So for example, it really depends on the direction the wind is. It depends on a lot of things. I can't answer that because that's not given in a scenario. But the velocities would definitely be different. The answer of which would be which depends upon more specific parameters. Okay? If it's a launch with some rotational inertia, if there's wind, if there's no wind at all, if there's no wind at all and these objects are not rotating whatsoever and they're all absolutely identical, then the third object would lose the most velocity because it's taking a longer path, right? That's where you could see that. Because it would have air resistance acting on it for a longer distance, so there's a good chance more work would be done, because work is force times distance times cosine theta. Longer distance, more work would be done by friction. Well,
so is rotational inertia the reason why they rifle gun barrels so that when the bullet leaves it's more stable?
That's exactly right. So an object, a bullet, when it leaves the barrel, spins this way, like about its axis. And that's why it's called a rifle. The gun barrel is rifled. That's the verb he's using there. Yeah, it's to add rotational inertia about whatever you might call this the z-axis if it's coming towards you. Okay. Yeah, muskets had just like what were they, like little not ball bearings, but like rocks or marbles in a sense. Were they called musket balls?
And there was no like.
Yeah, but I mean the actual shape itself too. That was a sphere, whereas a bullet it spins this way about. You want me to go over general stuff so you have an idea of everything that's on it? I mean, you know what's on it. 6, 1, 2, and 3. You could expect, just to give you a quick idea of format, the same, like 8 to 10 multiple choice, a couple short answer between like 3 and 6, meaning including A's and B's parts, and then between like usually 3 and 4 math problems. Mathematically, what are the 2 major theorems you should know? There are really 2 big theorems for the problems we've been doing. Yeah, mechanical energy conservation, MEI equals MEF. He was giving the more specific interpretation. And the second theorem from 6.2? That comes from the other formula. That comes from MEI equals MEF. There was another theorem completely. It was called something theorem.
I was gonna say like FT cosine theta for like work.
Yeah, good. So work, and what's the other part of the other theorem? The work what theorem? Work kinetic energy theorem. So we use work in that theorem, but we have to know those 2 theorems mainly. So let's go over them. So in 6.2 we had this theorem. And work, if we're not given the specific amount of work done, was defined as F d cos theta. So if you want to just find the work done on an object, you can just find F d cosine theta. That's what you can find to find the work done. Yeah?
Last one is just KE. Like, what's the?
So KE, delta simply means final minus initial. So the change in the object's kinetic energy is always equivalent to the amount of work done. So if I do 5 joules of work on this object, I know that it gained 5 joules of kinetic energy, assuming no friction. If it gained 5 joules of kinetic energy, it would gain velocity. So if there were no friction, what would this still be doing? It would still be moving. That's inertia. Inertia validates the work kinetic energy theorem. This is the final minus initial kinetic energy. So here's another interpretation. Let's say I gave you mass, final velocity, initial velocity. Instead, find the work done. You would go ahead and just simply use this part and not plug in for W, but instead plug in for your delta KE like this, and keep this as W. And then the next line would be okay? So that's what we would have. So if you're given mass and final and mass and initial velocities, why use FD cosine theta to find the work? Because work is equivalent to the change in kinetic energy. So if you could find the change in kinetic energy of an object, you know how much work is being done on that object. If an object speeds up, what kind of work is done on it? Positive or negative? But if it slows down, what kind of work? So if it speeds up, this final velocity, won't this be greater than this? When this number is greater than this number, you get a positive answer. It makes sense. But if your final velocity is lower than what you started with, aren't you slowing down? So if this is smaller than this, you're slowing down. Thus, you would get a negative answer, and therefore the work done would be the work done by friction or some opposing force, and therefore negative work. The work kinetic energy theorem needs to be known. If I didn't give you, or if I asked you, find the force of friction in this problem, you would have to go ahead and plug in FD cosine theta. And you'd have to plug in all this other stuff and then solve for F. That's the force of friction. You would have to be given the distance traveled. You'd have to plug in what for theta again, for friction? What's the full angle? 180. The whole angle of a straight line. And you could solve for the force of friction. You could even go as far as solving for mu, or Fn, or mg. mg goes here, remember? This becomes mu Fn. We did this in class like 4 or 5 times now. This is really mu Fn, but Fn is really mg in a lot of these problems because it's only horizontal motion. So this formula continues to break down further. But it depends on what I'm asking you for. Do you see what I'm saying? If I'm asking you for the coefficient of kinetic friction, that's mu. You'd have to be given the mass. You'd have to be given the distance traveled. Maybe not even given the mass, because on this side you have this. So the mass would cancel. So in these problems, maybe you're not given the mass and you're trying to find mu. Maybe you're not given the mass, you're trying to find the distance traveled, well then you'd have to be given mu. So it depends on what is asked. You need to know what variables mean. If I say find the coefficient of kinetic friction, you need to know that that is mu. And mu comes from Ff. It's mu Fn. Where does Fn come from? Fn is just mg because we have vertical equilibrium.
And to find mu, you would have like mg.
You'd have to be given, well, you not have to be given mass because mass would end up canceling in all these 3 terms. Okay? If that were broken down as far as that, I'm saying, okay? The other, yeah.
So that would mean that FF is basically just mu G, since mass comes.
It's not, no, because the mass is canceled, so you can't say that. It's only because mass is canceled. If instead of giving you this info, I told you the change in kinetic energy is 50 joules. Well, this would just be 50 joules. You wouldn't have the variables, and now you can no longer cancel mass. You'd have to include mass then. Mass has to be included. Because if I gave you, I said, it started with 10 joules of energy, and it ended with 60 joules of energy, other way around. It's friction. Started with 60 joules of energy, ended with 10 joules of energy. That'd be a change in 50, wouldn't it? So you'd plug in 50 here for delta KE. You wouldn't plug in the variables. Okay, and then you would have to still include mass. The other formula that you need to know, and this one again is the same thing. Draw a diagram for this one. Okay, it depends on the scenario. So let's just go through a couple of scenarios, all right? Let's do that real quick. Scenarios. We won't even do math. We'll just talk about scenarios and what this equation becomes. Scenario number 1. An object is on a cliff. It's compressing a spring, and it is launched eventually, ending on the ground. Energy to start. Energy to start. What kind of energy to start? Potential. It's not being thrown. It's being compressed to a spring. It's not being thrown. So no velocity. I'm not giving velocity. What else? Potential from height. What other?
Would there be like potential elastic?
Very good. Elastic potential because the spring is compressed. Whenever a spring is compressed, it's elastic potential. Very good. Now, where is it ending? Physically, where is it ending? Come on, respond. Just say it. On the ground. You guys know, you just answered this. On the ground. So there's no what if it lands on the ground? No potential. Potential is a function of height. What energy is a function of motion? And it's moving right before it hits the ground, isn't it? So this is kinetic. So scenario 1 becomes the following. To start, you've got elastic and you've got initial potential energy. And to end, you've got kinetic. So if you had a problem like this, that would be the equation you would use. Once you do this, all it is algebra. Substitute in the equation. Potential energy elastic, 1/2 kx squared. Potential energy due to height, mgy. Kinetic energy, 1/2 mv squared. These are on your formula sheet. If you could get to this line, you should get every problem right. Because at that point, all you're doing is plugging in formulas. You have to know what these variables are, right? Your initial height would have to be given. The K value. How do you know what K is? What are the units you look for K? Newtons per meter. As soon as you see newtons per meter, that's K. What is X? What is X? Came from the spring.
Y.
How far the spring is?
Being like stretched.
Yeah, or in this case, compressed. X is the change in the spring length due to compression or stretching. This is what you're answering here. This Y is the height here. Yi is the height. Mass obviously is mass. We all know that. Final velocity is the velocity with which it is about to hit the ground. What if instead of this, now change the scenario, find the velocity when it's 5 meters above the ground. Let's say the whole height was 36 meters. What would you do to change your problem to make life a lot easier? There's one big change you should make.
Would you just subtract like 5 meters?
Yeah, instead of making the height 36 meters, start the ground off at 5 meters and just subtract it.
And you also have
You could have also said at the end there's potential energy now. You can do that and add on PEF over here and call that potential energy a height of 5 at the end. But what I would do personally is recreate the ground and call this ground level. And therefore now my initial height is only, as Lauren said, the subtraction or difference of these two values.
So even if that were a two-part question, like you have to figure out.
If it's the second part, it would probably be easier to tack on the potential at the end and continue, I think, as a second part. But I'm saying if the problem were a brand new problem, I would do it this way because you don't have to worry about potential energy at the end of the problem by calling that the ground. How does the problem change if instead of being compressed on a cliff and launched, we need to focus, come on. Instead of compressed on a cliff and launched, it's now compressed on the ground and launched. Compressed on the ground and launched. It's just got elastic to start if it's compressed on the ground. Now, if it lands on a cliff and when it reaches the cliff, it's still moving because it's moving horizontally always, right? So it's still moving when it reaches the cliff. What kind of energy at the cliff does it have? Potential and kinetic. Yeah, pretty much you're moving the potential energy over. You took this and moved it over here. Because instead of starting on a cliff with potential, this problem now ends on a cliff. So I'm giving you this example now. Here's the spring compressed on the ground, and this object is being launched up to a cliff. So instead of starting on a cliff with potential and ending on the ground, so it started with potential and now it's got none, now here it's starting on the ground. So it's got no potential to start, it's only got elastic energy because of the spring, but it's ending at the cliff. It's still moving when it hits the cliff. It is, I'm assuming that. I'll make that clear. It still is traveling when it reaches the cliff height. So because it's still moving, when it gets to the cliff, this is the end of the problem, it's got kinetic. Because the cliff has height, it's also gained potential on the way up. What if the work done by friction is 3 joules on the way up? How do I incorporate that? If friction does 3 joules of work, so I lose 3 joules of energy as I'm traveling up to the cliff, how do I incorporate that in the problem? What do I do? What do I do? Same hands, same 4 or 5 people so far. Come on, somebody new. How would I incorporate friction in this equation? Where would it come about? You answer loud, but you can answer that again.
Q less and
Yeah, you tack on whatever is done by friction. I said 3 joules, so that would go right here. How does that make sense? I know it's weird because we know that work done by friction is negative. I've been putting absolute value around this on purpose. Why am I putting it on the right-hand side of the equation? Anybody know why I'm doing that? Think about it. If you're losing energy,
Well, it doesn't come into effect in the first part. It only comes into effect in the second part.
okay, as the traveling, you can think of it that way, but mathematically, give me a number. Give me a number. Starts with 10 joules of energy. If you're losing energy, what would the sum of these be then? Taking into account, what would the sum of these be? What would they? 7, because 7 plus 3 gives you. So, does it make sense to add it over here? Yeah, because you have less energy. You lost energy. Again, you start with 10 joules of energy. You lose 3. So either you got to put minus 3 over here, or tack on 3 over here. Because at the end of the problem, how much energy is left here? This is 7. Maybe it's like 4 joules of energy to the height, 3 joules of energy to the motion, and that came from the 10 joules of energy in the spring. Well, where are the other 3? There they are. This is the amount of energy lost to friction. That make sense what I'm saying? I might not make you do a lot of work because it's a test and you have time, so I'm probably going to give you a certain amount of energy. Instead of giving you like, the force of friction is this, find the distance traveled, and you have to use work equals FD cosine theta here. That was a lot of work. We did one of those examples, but that, with FD cosine theta, if that comes up, that would come up with work kinetic energy theorem. That's where that would play a role. For these problems, you can expect me to give you a value of energy lost due to friction. You need to incorporate it here by just tacking it on the right-hand side. George?
Are you going to have a choice of math problems? Or is it like...
I haven't made the math problems yet. So to be honest, I don't know. I'll probably give you a choice. I'll probably do like choose, I'll probably give you one and say choose 2 of the next 3. Okay? One that or maybe I'll give you 2 mandatory and make you choose 1 of 2 actually. Probably that. Because I want to see you do the work kinetic energy theorem. I want to see you use conservation of energy. Those 2 for sure. So those are going to be 2 questions guaranteed that you have to do pretty much. The third one I can make a choice out of 2.
Conservation of energy.
This is conservation of energy here, and then the previous slide we just went over was work kinetic energy theorem. Okay?
The multiple choice, which section did you say?
I'd say 6, 1, and 2 talks a lot about that. If you think about things like, I like to ask a lot of questions like, what happens to an object's kinetic energy if the speed doubles or triples? Or what happens to the potential energy if the height doubles or triples? I ask a lot of those, you know that. Questions about conservation for sure. So if you drop an object with 50 joules of energy and it lands with 40 joules of kinetic energy, what happened? And the 4 choices might one say, 10 joules of energy were converted to a spring. Well, there's no spring in the problem. 10 joules of energy would have lost the friction. That's probably the right answer. 10 joules of energy were converted to height. That doesn't make sense because it started at a height. So those are the kind of questions you can expect for those. Okay? Think outside the box, okay? Again, I put a recording up on Moodle of more example problems from 6.3. They're over there. I am also going to put a flow chart. Go to documents and handouts. There's a flow chart there right now to help you with problem solving. It includes power. Ignore power. We didn't cover 6.4 yet. Do your lab for Monday.
Sometimes are you gonna say like, are you gonna give us points for the diagram?
If I say draw a diagram and show the energies at each level, then I give you credit for it. You should do that always.
Yeah, sometimes like I do it, but like I wouldn't know how to do it. So like I see it in my mind, but I just can't like draw it. And then like I don't know, it's weird.
Practice over the weekend, 6.3 crop. So I recorded a bunch of example problems from 6.3 over the weekend.
Yeah.
Or not over the weekend, in the past that you can watch. They're out of that textbook over there. So if you want to borrow one of those for the weekend, that's what I think I mentioned to you yesterday, right? Yeah, I just don't know what problems there are.
Oh.
They're in the recording. It says like page 191 this. So if you want to sit in the recording and just fast forward through and get the problem numbers and take quick pictures, that's fine.
Yeah.
Okay?
Can I do my podcast?
Yeah, I have science club next door, so I'm not going to be here, but you can do it here. Yep.
To